solve this problem, live coordinated, my original solution I feel was a little bit inefficient when it came to space. It was still O of n when it came to time complexity, but space complexity definitely was O of n. And if I don't use any extra space, I can do it in O of one space. So we're gonna go ahead and start off this solution. So the first thing we want to do is just initialize some pointers. And so we're gonna go ahead and create some pointers. We're gonna start off with I. Let I equal m minus one. The reason I'm doing this pointers like that is because I'm actually gonna do a merge sort, but I'm gonna do it backwards. I'm gonna merge from the back. I'm gonna merge from the back of our array versus the front. So I'm gonna check which value is greater than, then I'll place it there, and I'll keep on going forth. So I'm gonna grab. So I just want to grab the last values in my array. So for I m minus one is gonna point to this value here. I have 3, and then I'm gonna do j is equal to n minus 1. So that tells me, okay, and this value of 2, this is the value that I'm pointing to. So 0, 1, 2, 3, but I do a minus 1, so I'm pointing to the index of 2 here. And then for I'm treating, we can think of it theoretically as another separate array. This entire array, because I'm thinking the way I'm applying it is I'm treating this like it's a different array, even though it's part of it, and I'm treating the entire thing as a separate array. So here, to get the pointer for to get the pointer for our last value in here, I do let p is equal to m plus n minus 1. So both of this added together is 6 minus 1 gives me the last value in here. 0, 1, 2, 3, 4, 5. I could have just done nums1 dot length, but I wanted to use all the values that were given to me. In my last solution, I didn't use m or n. I solved it, but I didn't use additional information, and I think that was a big difference in the optimal solution and the one that was still optimal when it comes to time, but not space. So, oh, I almost used a for loop there. We're gonna set up our while loop here. We're gonna set up our while loop, and our while loop is gonna check whether I is less than nums. Actually, no. Since we're going backwards here, we're checking if I is greater than or equal to 0. That's what we're checking for here, because this time we're not looking at the back, we're just checking from the beginning. So I is greater than or equal to 0. So as long as I is greater than or equal to 0, because we want to keep our while loop going. So the first condition in here that we're going to set up is we're going to check if nums of 1 is greater than nums. Oh, of course we got to put the brackets there. Nums of 1 of I is greater than nums 2 of j. So here we're comparing the last values in our array of 1, 2, 3, 2, 5, and 6. We're comparing 3 to 6, and we're seeing which one is greater. In this situation, 3 would be greater. So that would be handled by our else condition, where j has a greater value, or nums2 has a greater value. That's handled down here, where we do nums1 of p, which is pointing to our last value here of our zeros, because these zeros actually don't matter. I mean, they do matter, as in because they let us know where we can change values and it won't impact our answer. They're significant in that aspect, but we can replace them. That's why they're significant. It won't hurt our solution. So we do nums1 of p, and we equate to nums 2 of j. So we've done a successful replacement there. And then after we do that, we need to go ahead and decrease J minus minus because we're working backwards. So after we decrease J minus minus, we will always want to decrease P minus minus or P. This is pretty. In case you don't know this shortcut, this is the decrement. This is thing. There's an increment operator, but this is a decrement operator. All it is just saying P is equal to P minus one. That's just the shorthand way of writing that. And now we want to handle our if situation where nums one of I is actually greater than the nums two of J. So in that situation where that happens, we want to take nums one and equal it to nums one of P, because we only want to change these values back here. Well, we want to change these values for now. So we do that nums one of P, and we equate to nums one of I, and then we move, and then we advance down, and then we take I and decrement it as well, and then of course the P gets decremented automatically down here. So this algorithm should go through both our arrays until we get to until we get to a point where I is where I is less than where I is less than 0, or J is less than 0. So right now they're both greater than 0, and they'll keep on going until one of them becomes less than 0. And in that situation where one of them becomes less than 0, we want to handle it down here where we check, okay, so one of these values is less than 0, right? We're not, we're probably at this point, we can assume that if one of these values is less than the 0, it most likely in the situation where I'm trying to because in this situation, like let's say where we perfectly line up 1, 2, 2, and then 3 here, we realize, nums 1 of I is greater than 0 at that point, because we've probably decremented at least 4 times. We've decremented at least 4 times, so that just leaves us with 2, and then we have to just place the rest of them in there. So we can assume that it's the reason we can assume that our while loop is always going to we're always going to be dealing with J here is because if in a situation where in a situation where let's say J is the value that's the greatest, in a situation where like J has the lower values where it's like it's typing in. Now we need to check while J is greater than 0, we want to do nums 1 of P is equal to nums 1 of P is equal to nums 2 of J. And then we want to decrement J, and we want to decrement P. So this should be able to work, and we should be able to adjust our entire function. We should be able to adjust our entire function without having to create any excess memory. So we can run our code here, and let's see what happens. Oh, we have it. Oh, of course. A beginner mistake. Let's go ahead and run that again. And another one. Wow. Okay. What mistake did I make here? Okay. Line 18. The else statement. What's wrong with the else statement? If and then else, right? Line 18. Unexpected token. This is an unexpected token. It's weird. Why is it unexpected? Is it because I don't have it nested in there? Or if I have it like that, that's, oh, so it's just this. That's the problem. Do I have one too many curly brackets? Let's remove our curly brackets real quick and just analyze the situation. If that, and then I want to eclipse it in this, else I want to run this function. So let's close that off. Look at our while loop down here. That while loop runs there. That while loop runs there. That runs there. We run our code. Huh. Now I'm kind of now I'm stuck. Why is our code bracket appearing like it shouldn't be there? And if I remove it, I know that's still going to give me an error. Oh, I'm one too many minus variables there. I think that might have been causing our linter issue. Numbers one of p equals oh, and numbers two of I there. Oh man, that's numbers one. That's supposed to be numbers one. Oh, that's a lot of bugs. That's a lot of bugs. But okay, we run it through, and it looks like it works there, and it passes that test case. Now you might be wondering, why didn't I create a separate test case here for I? That's because J, in the situation where I still has values left, then 9 out of 10 they're already in the right order. 10 out of 10 they're in the right order. So in the situation, like let's do it. Let's put some test case. Let's put a test case in here where we know that that like let's like this, like if we do 7, 8, 9, we know that these are going to be the last values over here. So if it runs like this, it's going to compare. It's going to compare 9 and 6. It's going to place 9 there. It's going to compare 8. It's going to compare 8 and it's going to compare 8 and 6. It's going to place 8 there. 7 and 6. It's going to place 7 here, and then that leaves J. So 2, 5, 6. So that should also work. Where J is still our last value, even though it's the bigger one. And then if we look at another situation, we're like, okay, what if we do 1? We do 1 and another 1 here. We know these are going to be the first values. So all that is, it's just going to, okay, which one is greater, 1 or 6? 6 is greater, place it there. Which one is greater, 1 or 5? 5 is greater, place it there. Which one is greater, 1 or 2? 2 is greater, place it there. At that point, even though 1 is still greater than 0. I mean, even though 1, like at this point, our I is still greater than 0. We don't have to do anything because at that point we can assume it's sorted. Because if J is empty and I is left in place after all its values have been compared, and none of them were ever, and none of the values in I were greater than the values in 2, we can assume that it's ordered and it's already taken care of for us. So we don't need to check I. We can just need to check J. So we can run this code to run it. And that worked perfect. So we're going to go ahead and submit this code. And there we go. It passed a runtime of 52%, 33.9 megabytes. And we can go ahead and close this out. If you have any questions, please let me know in the comments below.